Rust has continuously evolved ever since version 1.0 was released in 2015. We've added major features such as the try operator, const generics, generic associated types, and of course async await. Of those 4 features, 3 are what can be considered to be effects. And though we've been working on them for a long time, they're still very much in progress. Hello, my name is Yash, and I work as a developer advocate for Rust at Microsoft. I've been working on Rust for the past 5 years, and among other things, I'm a member of the Rust Async Working Group and the co-lead of the Rust Effects Initiative. The thesis of this talk is that we've unknowingly shipped an effect system as part of the language since Rust 1.0. We've since begun adding a number of new effects, and in order to finish integrating them into the language, we need support for effect generics. In this talk, I'll explain what effects are, what makes them challenging to integrate, and how we can overcome those challenges. When I first started with Rust, it took me a minute to figure out how to use generics. I was used to writing JavaScript, and we don't have generics there, so I found myself mostly writing functions which took concrete types. I remember my code felt pretty clumsy, and it wasn't a great experience, at least not compared to code I was using from the standard library. An example of a generic standard library function is the IOCopy function. It reads bytes from a reader and copies them into a writer, and we can give it a file, a socket, or any combination of the two, and it will happily copy bytes from one into the other. This all works as long as we give it the right types. But what if Rust actually didn't have generics? What if the Rust I used to write at the beginning was all we had? How would we write IOCopy? Well, given we're trying to copy bytes between sockets and files, we could probably hand code individual functions for these. For our 2 types, we would end up with 4 unique functions. Unfortunately for us, that would only solve the problem right in front of us. The standard library doesn't just have 2 types which implement read and write, it has 18 types which implement read and 27 types which implement write. So if we wanted to cover the entire API space of the standard library, we'd need 486 functions in total. And if that was the only way we could implement IOCopy, that would be a pretty bad language. Now, luckily Rust does have generics, and all we ever need is the one copy function. That means we're free to keep adding more types into the standard library without having to worry about implementing more functions. We just have the one copy function, and the compiler will take care of generating the right code for whatever type we give it. Types are not the only things in Rust we want to be generic over. We also have const generics, which allow functions to be generic over constant values, as well as value generics, which allow functions to be generic over different values. This is how we can write functions which can take different values, which is a feature present in most programming languages. But not everything that can lead to API duplication are things we can be generic over. For example, it's pretty common to create different methods or types depending on whether we take a value as owned, or as a reference, or as a mutable reference. We also often create duplicate APIs for constant values and for runtime values, array versus vec, as well as create duplicate structures depending on whether the API needs to be thread safe or not, and so on. But out of everything which can lead to API duplication, effects are probably one of the biggest ones. When I talk about effects in Rust, what I mean is certain keywords such as async await and const, but also question mark, and types such as result or option. All of these have a deep semantic connection to the language, and they change the meaning of our code in ways that other keywords and types don't. Sometimes we'll write code which doesn't have the right effects, which leads to effect mismatches. This is also known as the function coloring problem, as described by Robert Nystrom. Once you become aware of effect mismatches, you start seeing them all over the place, and not just in Rust either. The result of these effect mismatches is that using effects in Rust essentially drops you into a second-rate experience. Whether you're using const or async, result, or option, almost certainly somewhere along the line you'll run into some kind of compatibility issue. Take, for example, the option filter API. It takes a closure, which takes a type by reference and returns bool. If we try and use the try operator inside of it, the compiler will give us an error because the closure doesn't return result or option, it returns bool. Not being able to use the try operator inside of arbitrary closures is an example of an effect mismatch. But simple functions like that only scratch the surface. Effect mismatches are present in almost every single trait in the standard lib2. Take, for example, something common like the debug trait, which is implemented on almost every type in Rust. Say we wanted to implement a debug trait for our made-up type cat. She's asleep. The parameter f here implements IOWrite and represents a stream of bytes. Using the write macro, we can write bytes into that stream. But if for some reason we wanted to write bytes asynchronously into, say, an async socket, well, we can't do that. Function format is not an async function, which means we can't use await inside of it. One way out of this could be to create some kind of intermediate buffer and synchronously write data into that. We could then write data out of that buffer asynchronously, but that would involve extra copies we didn't have before. If we wanted to make it identical to what we were doing before, the solution would be to create a new async debug trait, which can write data asynchronously into the stream. But we then have duplicate traits, and that's a problem worth avoiding. It's tempting to say that maybe we should just add the async debug trait and call it a day. Maybe we can also add async versions of read, function, write, function once, iterator, hash as well, since it too writes to an output stream, function mute, maybe from and into as well, drop. These are all language built-ins, and so on. The reality is that effect mismatches are structural, and duplicating the API surface for every effect mismatch leads to an exponential explosion of APIs, which is similar to what we've seen with data type generics earlier on. Let me try and illustrate this for a second. Say we took the existing family of function traits and introduced effectful versions of them. That is, versions which work with unsafe, async, try, const, and generators. With one effect, we're up to 6 unique traits. With 2 effects, we're up to 12. With all 5, we're suddenly looking at 96 different traits. The scope of the standard library is really broad. From analyzing the Rust 170 standard lib, by my estimate, around 3/4 of the standard library would interact with const, around 2/3 would interact with async, and around 1/3 would interact with try. Maybe more, it depends. So the exact numbers are imprecise because parts of the various effects are still in progress. We're still designing them. So how much this will end up being in practice will depend on how we design the language. If you compare the numbers, then it appears that close to 100% of the standard library would interact with one or more effect, and around 50% would interact with 2 or more. If we consider that whenever effects interact with each other, they can lead to exponential blowup, it should warn us that clever one-off solutions probably won't cut it. I believe that effect mismatches are a structural problem, and in order to solve it, we need structural solutions. And the best option we have is to enable Rust to be generic over effects. Now that we've taken a good look at what happens when we can't be generic over effects, it's time we start talking about what we can do about it. The answer, unsurprisingly, is to introduce effect generics into the language. To cover all uses will take a few steps, so let's start with the first, and arguably most important one, effect generic trait definitions. These are important because they would allow us to introduce effectful traits as part of the standard library which would, among other things, help standardize the various async ecosystems on the standard library. Let's use a simple example here, the into trait. The into trait is used to convert from one type to another. It is generic over a type T and has one function into, which consumes self and returns the type T. Say we have a type cat, which when it takes a nap, turns into a cute little loaf. We can implement into loaf for cat by calling self.nap in the function body. Isn't that right? But what if the cat doesn't take a nap straight away? Maybe nap should actually be an async function. In order to await nap inside the trait impl, the into method would need to be async. If we were writing an async trait from scratch, we could do this by exposing a new async into trait with an async into method. But we don't just want to add a new trait to the standard lib. Instead, we want to extend the existing into trait to work with the async effect. The way we could do this is by making async optional. Rather than requiring that the trait is always sync or async, implementers should be able to choose which version of the trait they want to implement. The way this would work is by adding a new notation on the trait, maybe async. We don't yet know what syntax we want to use for maybe async, so in this talk we'll be using attributes as a placeholder. The way that maybe async notation works is we mark all methods which want to be maybe async with the attribute, and then we mark the trait itself as maybe async as well. Implementers then get to choose whether they want to implement the sync or async versions of the trait. Depending on which version they choose, the methods then end up being either sync or async. This system would be entirely backwards compatible because implementing the sync version of into would remain the same as it is today. The people who want to implement the async version would be able to just by adding a few extra async keywords to the impl. Under the hood, the implementations desugar to regular Rust code we can already write today. The sync implementation of the type would return a type T, but the async impl would return an impl future of T. Under the hood, this is just a single const bool set to true or false, and an associated type. So it would be reasonable to ask why we're bothering with a language feature if the desugaring ends up being so simple. And the reason is, effects are everywhere, and we want to make sure that effect generics feel like they're part of the language. This not only means tightly controlling diagnostics, we also want them to be gradually introduced, have clear language rules, and be backwards compatible. But if you keep all that in mind, it's probably fine to think of effect generics as mostly syntactic sugar for const bools and associated types. Being able to declare effect generic traits is only the beginning. The standard library not only exposes traits, it also exposes various types and functions. And effect generic traits don't directly help with that. Let's take our earlier IO copy example again. As we've said, copy takes a reader and a writer and then copies bytes from the reader to the writer. Now, what would it look like if we tried adding an async version of this to the standard lib today? We'd need to start by giving it a different name, so it doesn't conflict with the existing copy function. The same goes for the trait bounds as well. So instead of taking read and write, this function should take async read and async write. Now things get a little better once we have effect generic trait definitions. Rather than needing to take async duplicates of the read and write traits, the function can instead choose the async versions of the existing read and write traits. That's already better, but it still means we have two versions of the copy function. Instead, the ideal solution would be to allow copy itself to be generic over the async effect, and make that determine which versions of read and write we want. These are what we call effect generic bounds. The effect of the function and the effect of the bounds it takes all become the same. In literature, this is also known as effect row polymorphism. Because the function itself is now generic over the async effect, we need to figure out at the call site which variant we intended to use. This system will make use of inference to figure it out. That's a fancy way of saying that the compiler is going to make an educated guess about which effects the programmer intended to use. If they used the wait, they probably wanted the async version. Otherwise, they probably wanted the sync version. But as with any guess, sometimes we guess wrong, and so for that reason, we want to provide an escape hatch by enabling program authors to specifically declare the variant. We don't know what exact syntax we want to use for this, but we probably want to base it on a turbofish notation. We'll start there. But effect generics aren't just needed for functions. If we want to make the standard library work well with effects, then types will need effect generics too. This might seem strange at first, since an async type might not be very intuitive, but for example, files on Windows need to be initialized as either sync or async, which means that whether they're async or not isn't just a property of the functions, it's a property of the type. Let's use the standard library's file type as our example here. For simplicity, let's assume it has a single method, open, which returns either an error or a file. If we wanted to provide an async version of file, we again would need to duplicate our interfaces. That means a new type async file, which has a new async method open, which takes an async version of path as an argument, and path needs to be async because it itself has async file system methods on it. So as I've said before, once you start looking, you notice effects popping up everywhere. Instead of creating a second async file type with effect generics on types, we'd be able to open file as async instead, allowing us to keep just one file definition for both sync and async variants. Now, so far, I've sort of hand-waved away the internal implementations of both the copy function and the file type. The way they work is a little different. In the case of the copy function, the implementation between the async and non-async variants would be identical. If the function is compiled as async, everything would work as written. But if the function compiles as sync, then we remove the awaits and the function should just compile as expected. As a result of this, maybe async functions can only call synchronous functions or maybe asynchronous functions inside of their bodies. But that should be enough for most cases. Now, concrete types like file are a little trickier. They often want to run different code depending on which effects they have. Luckily, types like file already conditionally compile heaps of different code depending on the platform. So if we introduce new conditions for async or not, that wouldn't be too big of a jump. The key thing we need is a way to detect in the function body whether code is being compiled as async or not, which is basically a fancy bool. We can already do this for the const effect using the const eval select intrinsic. It's currently unstable and a little verbose, but it works reliably. We should be able to easily adapt it to something similar for async and the rest of the effects too. Research on effects has been a topic in computer science for nearly 40 years. That's about as old as C++ is. It's become a bit of a hot topic recently in PL spheres, with research languages such as Coca, F, and Frank showing how effects can be useful, and languages such as Scala, and to a lesser extent Swift, adopting effectful features. When people talk about effects, they will broadly refer to one of two things. Either algebraic effect types, which are semantic notations of functions and contexts that grant permissions to do things, or algebraic effect handlers, which are a kind of typed control flow primitive that enables people to write their own versions of async await, try catch, yield, and so on. A lot of languages which have effects provide both effect types and effect handlers. These can be used together, but they are in fact distinct features. What we've been calling effects in this talk so far have in fact been effect types. Rust hasn't historically called them this, and I believe that's probably why effect generics weren't on our radar until recently. But it turns out that reinterpreting some of our keywords as effect types actually makes perfect sense and provides us with a strong theoretical framework for how to reason about them. In Rust, we currently have 5 different effects. async, unsafe, const, try, and generators. All 5 of these are in various stages of completion. For example, async Rust has async functions and blocks, but no async iterators or async drop. Const doesn't have const traits yet. Unsafe functions can't be lowered to unsafe event traits. Try has the question mark operator, but try blocks are unstable. Generators are entirely unstable, and we only have the iterator trait. Some of these effects are what folks on the Lang team have started calling carried. These are effects which will desugar to an actual type in the type system. For example, when you write async fn, the return type will desugar to an impl future. Some other effects are what we're calling uncarried. These effects don't desugar to any types in the type system, but serve only as a way to communicate information back to the compiler. These are, for example, const and unsafe. While we do check that the effects are used correctly, they don't end up being lowered to actual types. When we talk about carried effects, effect composition becomes important. Take, for example, async and try together. If we have a function which has both effects, what should the resulting type be? Is it a future of result or a result containing a future? The answer is it should be a future containing a result.
But why?
Effects on functions are order-independent sets. While Rust currently does require you to declare effects in a specific order, carried effects themselves can only be composed in one way. When we stabilized async await, we decided that if an async function returns a result, that should always return an impl future of result. And because effects are sets and not dependent on ordering, we can define the way carried effects should compose as part of the language. People can still opt out from the built-in composition rules by manually writing function signatures. But this is rare, and for the overwhelming majority of uses, the built-in composition rules will be the right choice. The const effect is a bit different from the other effects. Const blocks are always evaluated during compilation, while const functions merely can be evaluated during compilation. It's perfectly fine to call const functions at runtime too. This means that when we write const fn, we're already writing effect generics. This mechanism is the reason why we've been able to gradually introduce them into the standard library in a backwards compatible way. Const is also a bit strange in that it disallows certain things. For example, const functions can't access the host runtime. They can't allocate. They can't access globals. This feels a little different from, say, async, which feels like it only allows you to do more things. What's missing from this picture is that all functions in Rust carry an implicit set of effects, including some effects we can't directly name yet. When we write const functions, our functions have a different set of effects than if we write no-std functions, which again are different from regular std Rust functions. The right way of thinking about const, std, etc. is as adding a different set of effects to the empty set of effects. If we start from 0, then all effects merely add to the set. Unfortunately in Rust, we can't yet name the empty set of effects. In effect theory, this is called the total effect, and some languages, like Coca, support it. In fact, Coca's lead dev has estimated that around 70% of a typical Coca program is total. So far, we've only talked about how we could finish the work on existing effects, such as const and async. But one nice thing of effect generics is that they would not only allow us to finish our ongoing effects work, it would also lower the cost of introducing new effects into the language, which opens up the question, if we could add more effects, which effects might actually make sense to add? The obvious ones would be to actually finish adding try and generator, etc. But beyond that, there's some interesting effects we could explore. For brevity, I'll only discuss what these effects would do and not actually show code examples, but bear with me because there's a number of them. No divergence would guarantee that a function cannot loop indefinitely, which would open up the path to perform static runtime cost analysis. This is useful for platforms like BPF or real-time operating systems, which have hard execution guarantees. No panic would guarantee that a function would never produce a panic, which means a function would never unwind. This is useful because unwinding is a control flow path, and no panic would remove that entirely. Parametricity is a fun effect. It guarantees that a function can only operate on its arguments. That means it wouldn't implicitly access statics, no global file system, no thread locals, only the function arguments. Destructor linearity is another fun one. It would guarantee that drop is always called. Pattern types would enable functions to operate directly on variants of enums and numbers. You can think of pattern types as a form of lightweight formal verification. These are also known as liquid types. Though there's nothing inherently stopping us from adding any of these features into Rust today, in order to integrate them into the standard library without breaking backwards compatibility, we need effect generics first. This brings us to the final part of the design space: effect aliases. If we keep adding effects, it's very easy to eventually reach a situation where we have our own version of public static void main. In order to prevent that, it would instead be great if we could name specific sets of effects. In a way, we've already done that, where const represents may loop forever plus may panic. If we actually had may loop forever and may panic as built-in effects, then we could rethink const as instead being an alias of those two effects. Fundamentally, this doesn't change anything we've talked about so far. It's just that effect aliases would syntactically be a lot more pleasant to work with. If we ever reach a state where we have effect generics and we notice we maybe have too many notations in front of our functions, maybe const, maybe async, maybe try, plus maybe, I don't know. At that point, it may be time for us to start looking into effect aliases more seriously. So, to recap what we've talked about today, Rust already includes effect types such as async, const, try, and unsafe. Because we can't be generic over effect types yet, we usually have to choose between either duplicating code or just not addressing the use case. And this makes for a language which feels incredibly rough once you start using effects. Effect generics provide us with a way to be generic over effects, and we've shown that they can be implemented today as mostly syntactic sugar for const generics and associated types. We're currently in the process of formalizing the effect generics work via a mere formality. Mere formality is an in-progress formal model of Rust type system. Because effect generics are relatively straightforward, but have far-reaching consequences for a type system, they're an ideal candidate to validate using formal methods. In parallel, the const working group has also begun refactoring the way const functions are checked in the compiler. In the past, checking happened right before borrow checking at the mere level. In the new system, const checking happens much sooner at the here level. This will not only make the code more maintainable, it will also be generalizable to more effects if needed. Once both the formal modeling and compiler refactorings conclude, we'll begin drafting an RFC for effect generic trait definitions. We expect this to happen sometime in 2024. And that's the end of this talk. Thank you so much for being with me all the way through to the end. We covered some theory. I hope it was interesting. None of the work in this talk would have been possible without the following people. Ollie, who is the co-lead of the Effects Initiative and who came at this from a const angle. Eric, who's my colleague, and we've spent so many hours talking about effects and wondering, like, can we do more? Nico, who is the advisor of the Effects Initiative from the Lang team, who sat down with us and actually vouched for us that, hey, maybe this is worth investigating. And Dan, who is the creator of Coca, leading expert in effects, and, has spent hours and hours sitting with us, just being like, hey, I'm willing to walk you through everything effects. And yeah, everyone's been so generous. It's been great. Thank you.